Good afternoon. I'm very pleased to be here. Unfortunately, the presentation was in English, so it will be really awkward just to have an English background and speaking in Turkish. Just for the sake of consistency, I believe it will be better to proceed with English presentation. Let me introduce myself. I'm a faculty member in two different programs of Sabancı University Faculty of Engineering and Natural Science. One is Material Science and Engineering, another one is Manufacturing Engineering. And also I'm a founding director of Composite Technologies Center of Excellence with an industrial collaboration with Sabancı Holding Company, Korsa. So I will be talking about one of the research activities for some time that we have been performing. And also I will spend some time just to be able to introduce the capabilities that we do have in relation to composite materials and the processing technologies in the coming slides. This work was initially actually done one of my former PhD students. Now he's a research fellow in our group, Mr. Sanjani. And these are the collaborators. And it's effectively the culmination of the several works. It is not a single work that we published, and they are open available in existing literature. So this is, first I will just proceed with our capabilities, what we do have and what we do at Sabancı University in relation to composite materials and the composite technologies. And then later on I will, after just the 10 slides, I will directly get into the scientific part of the presentation. So this is basically the building that we do have the Integrated Manufacturing Technologies Research and Applications Center that is well recognized by Higher Education Institute of Turkey. And also this center has an industrial collaboration with a company, and then we do have our joint work as the Composite Technologies Center of Excellence. Effectively, that collaboration creates an ecosystem where industry and the university coexist in the same building, in the same environment, so they just basically bring their powers to be able to proceed towards the future in terms of developing composite-related technologies. So the idea is to create such a collaboration in relation to the composite technologies, is to create an environment where complex, multifunctional, smart composite materials can be produced up to the TRL level of from the university side to 6. Like normally, if you refer to the capabilities of the universities, generally the research is initiated, and also it mainly targets the technology readiness level up to 3. And when we look at the industries, of course, they are driven by the money making, and they don't have much time for the dedicated research, and their technological readiness level targets from, let's say, that 7 to 9. Actually. But there is a gap that nobody claims, and actually which is very challenging to claim because it's the value of debt. And then the university doesn't have that motivation, company doesn't have that time to able to dedicate the research activities and the human resources, and that gap needs to be covered to be able to make a transformation actually in the industry. And this is actually the challenge that we embrace. And with that one in mind, we said that, okay, we do have accumulated the critical mass in our university. And now we have a good, the capabilities in terms of the high quality human resources, infrastructure. Why don't we bring that, basically the powers, and create a synergy such that the entire value chain of the composite technologies can be well covered? Actually, that was the main incentive behind this endeavor. So with that, we basically create a center on 3 pillars. And one of the pillars is naturally technology build-up and the capacity build-up, and which is not focusing on everything, but certain aspects. And these are advanced composite technologies, micro-nano manufacturing, additive manufacturing, and the robotic-based unconventional manufacturing. So these are basically the focus of interest. And of course, these technologies should have applications and the commercializations. And the university naturally will not be able to do it by itself. So that should be done with industry. And for that, to be able to do so, beyond going the words, you have to actually live by the industry. So under the same ecosystem and should bear the same pains they go through. And for that, we basically focus on the technology development in the fields of aerospace, defense, automotive, through covering the stages from design to production. And of course, the most important asset of any setting is the human resources. You can just buy all the equipments, make all the investments, but if you don't have the high quality, the personnel behind that, if you do not train it or upscale it or reskill it, then all the effort is going to be dead to begin with. So then we do basically put a lot of focus on training of high quality personnel through research, and then also foster the entrepreneurship. And just to integrate all these pillars under the same roof within the framework of university-industry collaboration in the fields of integrated manufacturing and composite technologies. Oops. Now, if you look at a little bit closely, what we want to, there are critical mass and interest. We do have strong focus on advanced composite technologies and additive manufacturing in combination with the unconventional manufacturing. It can be robotic-based or non-robotic based. And then we do have our critical mass in relation to tailoring the properties of composite related to micro-nano integration. So these are the capabilities, and the main umbrella is the Sabancı University Integrated Manufacturing Center. And that integrated manufacturing center has actually the industrial legs, I may say, as an analogy. And within the fields of composite material technologies, we do collaborate with KORTSA in a dedicated directed research, and we do have another partner on metal-based additive manufacturing technologies. So the center has its own, not only project-based, but vision unified legs with the industry. So this is effectively the model that we created. So when we look at the entity, the physical entity, it is located in Teknopark, Istanbul. It is in Anatolian side of Turkey, which is very close to the Sabiha Gökçen Airport. I think by car it is 1 minute. If you just want to walk, 5 or 10 minutes. So, the available facility is 15,000 meters square closed area, and then around 5 to 6 meters, the 1,000 meters square is dedicated to the research. And it's a 5-story buildings, 2 stories. The story belongs to the Sabancı University. Another one is KORTSA Global. 2 entities, they live in the same center. And they do have their own manufacturing facilities, and we do have the center that we closely cooperate. Of course, our interaction is not limited because as a university, we are a neutralized institute, so we can cooperate that we have been doing so far with another, the industry in relation to, within the framework of the center, with the composite technologies and the manufacturing technologies. So, as I just basically mentioned, the KORTSA has its own the production facility and their R&D center. We do have the center and also university to be able to access to the human resources and train them. We do have in the same building our manufacturing engineering master and PhD programs that we do basically trains the employees of the company that want to do PhD or master or the MSc studies, and we do have our incubation centers. So if you just look at a little bit closely, the center is being contributed by the 20 faculty members and researchers in the field of integrated manufacturing with a background of chemistry, aerospace, mechanical engineering, robotics, and electronic engineering. So it requires disciplines or the expertise from the different disciplines. And also we do have the available space to be able to accommodate 90 PhD students. Currently our number is around 30 PhD students that they do have at the center. And we do have incubation environments, and we do have several meeting rooms and 2 classrooms and 1 conference hall. So this is in a way a center that combines or that brings the industry, university education, and post-5 level manufacturing under the same umbrella. So this is the setting that we do have. And this is the building that just basically is an entity that is located in Technopark, Istanbul. The system just offers a platform for open innovation. It means that we do not want this one to be only the center of Sabancı University, rather just to create an open platform so that anybody who is basically dedicated himself or herself to the research in the field of integrated manufacturing and composite technologies can come and do collaborative work at the center. So that we want it to be like basically effectively towards the future as the national composites, the technology center of excellence of this country. So that is the whole idea, so that it will just go beyond the Sabancı University and its entities, so that the facility can be used better in terms of its capabilities. So if you look at the closely, what we do have is we have 10 laboratories, and these are effectively not the university level labs, but more in the level of prototype manufacturing. So it can do fundamental research, but it can do in the fields of composite technologies, the prototype level manufacturing. Starting from the polymer processing all the way to design and manufacturing large-scale components. When I say large-scale, the center will be able to manufacture a part, for example, let's say the 5 meter by 3 meters. So it's a rather big part when we consider the composite materials. Of course, not in the scale of mass manufacturing. So we have wet chemistry, material characterization, polymer processing, additive manufacturing, robotic manufacturing, advanced composites, mechanical characterization, clean room, autoclave, and the 10th one is multi-scale design and engineering. So that is, the center has high-performance computing facilities that can be used to be able to make design and manufacturing at the center. I'll just skip this one. This is effectively shows some of the distribution of the labs that you see. These are the offices, office spaces, and these are the labs what we have that we will get into some of the pictures. This is, for example, some pictures from the wet chemistry lab. It is quite well equipped with the relative equipment that is needed to be able to do the polymer processing, polymer synthesis, and it has all the necessary facilities to be able to accommodate such research for both fundamental science perspective and also the prototyping level. Sometimes. And this is material characterization laboratory that can do all the tests in relation to the polymer processing. For the polymer synthesis, like different DSCs, DNAs, TGAs, the HDV cats. So it is a quite sophisticated lab in terms of the capabilities, and which is open to the services of all the stakeholders from the universities and also from the industry. So it gives, and also it will start giving by the end of this year, accredited testing services as well in relation to the AS 9100 and the ISO 17025. This is our polymer processing laboratory that we have both the small lab scales and the larger scales, the systems that we can do for the polymer processing. And this is our mechanical characterization and non-destructive testing systems that we cover from different ranges, and then the system can deliver aerospace the level testing services. And it has the fatigues, the axial, the biaxial fatigues, including the axial and torsion. So it is quite advanced facilities that we do have. You see that equipments are not the lab scale system, is more on they can do component tests as well. And some of also we can do the cutting, trimming, preforming in relation to the textiles. So this is one of our machines that we can do, cut the fibers and also cut the dry composites as well. And these are some of the aisles, and then this is one of the systems. Some of the additive manufacturing systems, they arrived, but we did not install yet. But we do have two big additive manufacturing systems that we can manufacture large-scale metal bases. And also we do have robotic systems that we designed to be able to do do the large-scale printing on robots. So this is the capabilities. And also the center, these are some offices for the PhD students and the engineers. And also at the center, this is one of the facilities that we can do the fiber placement for aerospace manufacturing. So this robot here, that is going to be the system that can produce a part up to 6 meters by 3 meters, and it can just place dry fiber, the thermoset, and thermoplastic. So these are, in a way, some of the very snapshot of the capabilities that we do have at the center. I'll just skip this one. This shows some of the capabilities in a nutshell in terms of the level. And some of the industries that we basically, the target is basically aerospace, automotive, and the marine and the transportation. So we do have active researches that targets this applications. And this is in a way a commercial in terms of the capabilities. Now we can get into actually one of the example research in relation to what we do at the center. And that is going to be nano-engineered multi-scale reinforced smart and responsive polymer composites. The title is quite long, but what we want to imply is that we can engineer composites. They can be responsive, they can be smart, and then we can, by nano-integration, we can improve and tailor their mechanical properties. So this is going to be the scientific part of my talk. I will skip this part because since this is a composite community, it is going to be quite redundant just to describe what the composite is. But when the presentation is given to a different audience of backgrounds, then it will be always good to have an introductory page. But just with your permission, I would like to just skip this one and noting that this is already well known to the community here. So what we actually did in this work, and we know that the carbon fibers, the gentleman just before me, he just basically gave a market analysis, nicely introduced, and it has been used for aerospace industry, and also now it is being uptaken by the automotive, although the price is an issue. Now when we look at the aerospace industry, the material properties cannot be further improved. But still we want to make the structure lightweight and then just to be able to have a better performance using less material. Since you cannot control much the carbon properties anymore, you have to do something else. And of course, nanotechnology, it has been some time a buzzword among the scientific community, but it has been penetrating into the structural materials as well. And we try to combine the graphene into the composite material, but not arbitrarily, just basically not mixing them in an ad hoc manner, but rather just basically doing the engineering aspect. If that can be incorporated smartly, then we will be able to improve the performance of the material better. So this is going to summarize it. So what are the attributes of the graphene? Of course, this is a pure single sheet graphene. It is one of the strongest materials. And then when you look at here, Young modulus is incredible. And the ultimate strength, it is huge. And also it offers you enormous specific surface area. And then if they can be incorporated into the composite, it will be able to give you different attributes. For example, flame retardancy. And because of this one, it can be used in aerospace, construction, battery, textile, and wood. And then we just basically in this work focus on the textile industry for aerospace application. And what we have done is that we just basically start with the carbon fiber here, and these are the properties of carbon fiber. And we combine the carbon fiber with graphene, not basically mixing it in an ad hoc manner. So we integrate it onto the fabric and also onto the resin material. But of course, it is not a mere integration. The surface needs to be functional so that your graphene is going to communicate with your carbon fiber and the epoxy by forming covalent bonding. It's not going to be only a mechanical joining process. And these are the graphanes that we basically produce at the center. And now we have a spin-off company called the nanographane that we can produce thermally exfoliated graphanes, and it is being formed by multi-layers. If they can be sheared, that can be reduced into a single sheet, so that you can increase the surface area of the material. And what we have done is that just first we try to improve the mechanical performance of the resin. We just mix them, and of course by just functionalizing the graphene properly with the epoxy resin, and then under the high shear mixer, and then we'll just make a classical molding. And of course, which is basically the here classical molding, and later on we integrate it onto the composites, into the matrix as well. First, I will just talk about the results of this one, and then you may say that anything that you add is going to improve the performance of the composite, so what is new about it? That might be a very logical question, because you are adding a reinforcement and you see that this is the neat material, and then you are increasing the mechanical performance because you are increasing the toughness of it. Because effectively the epoxy is a very brittle resin, and then when you add the graphene, it creates basic obstacles for the crack to propagate. And then you are increasing the toughness, and this is what you have. And then you see that the strength can be improved with the amount of 0.05 weight percent. And we see that adding beyond that is not going to make any changes. This is effectively your percolation threshold. And one can find a lot of basically the literature activities in that. And this is the neat one, and you see that it is very the clear surface, like your material is cleaved. And then here, this is the very ductile fracture. Your graphene pins the crack propagation and then increase the mechanical performance of your material of the matrix. And we said that that is fine. So this is what we achieved, is already achieved by the people by adding different amounts of material. But our main interest is to be able to increase the performance of the composite. That is very challenging, because you have already fiber reinforcements, either carbon fiber, glass fiber, very, very strong. You have to do really smart things so that the improvement will exceed the reinforcement that will come from it. So we said that we will incorporate this one first onto the textile. We create a suspension of the graphene, and then there are different methodologies. Either you can basically spray it onto the surface with the airbrush, but then you will have a droplet size very big, so that you will have an agglomeration. And instead, to be able to beat the surface tension, we said that we should use electric field, because electric field acts in an opposite direction to the surface tension. So you form a tidal cone that gives you a very refined jet, so you can just distribute your graphene in a very controlled manner. So that is the reason we incorporate it to the surface of our material, and you see that these are the attachment of the graphene sheets to your carbon fiber, and this is zoom out view, and it is nicely covered. We also integrated this graphene into the epoxy as well. And we produce composites, neat composites, matrix reinforced one, only textile reinforced one, and the hybrid reinforced one, meaning that including both textile and the matrix. And this is the methodology of the electrospraying, so you create a potential difference, so you create a tidal jet, so that you have a very fine atomization. And then we, of course, look at, just to basically prove our claim that we cover the surface nicely, one should look at the Raman of the surface, and you see that by the Raman spectroscopy, we can easily show by comparing the D-band and G-band intensity, and we can show that we were able to cover the surface of our material, and also just to basically ensure that this is not going to lead us in a wrong direction. We look at also the XPS rate. And this is a facility that from the Koç University that they kindly performed this test for us. And then we just basically looking at the SP2 bands. We basically show that our material is well covered by the thermally exfoliated graphanes. So these characterization tools are performed to be able to prove that we can nicely cover the surface of our material. And we look at actually flexural strength. And then if you look at here, this is CFRP, carbon fiber reinforced plastic, in a solo manner, which is neat one. And then if you add certain amount of graphene to the interface, meaning that only to the textile, this is the improvements we have. And then if you add to the matrix, the red one, but if you reinforce both the interface and the matrix, the improvement is significant. So this is, you see that when a system needs to be reinforced for the composite, it's not going to be enough only just to reinforce the interface, but you have to reinforce the matrix so that there will be a continuous force transfer. Otherwise, you will not be able to see the improvement at all. And these are some of the improvement, and you see that for this hybrid system, improvement is immense. This is far exceeding any data reported in the literature, considering the amount of material that we are adding. 52% is a huge improvement that we are getting without increasing the amount of carbon fiber reinforcement or increasing without increasing the lamination. For this is for us, it was a percolation threshold. If you add above that one, it's not going to bring you any advantage. And then we basically look at in detail actually the fractured surfaces, and you see that this is the neat one and it is being delaminated because you have a big interface. And then if you improve the interface is strengthened, so there is no obvious delamination. This is matrix reinforced, and then it prevents the cracks in the matrix with respect to the others. And this is both interface and the matrix, and there is the delamination, but this happens far beyond the force that we applied onto this one. So you are increasing the performance of your matrix and also increasing the performance of the interface. And of course, we look at the tensile properties. The improvement is not that significant because the primary load-carrying agent is the carbon fiber reinforcement. So although there is improvements, if you look at here around 20%, but in comparison to the flexural, still it is half of it. So the addition of the nano-integration, if you do that on an engineered box, the aim should be increasing basically the flexural strength, toughness, and also impact attributes, not the tensile property. So this is the takeaway lesson that we can basically mention. Also, to be able to characterize, we just look at the Poisson ratio. If you look at here, by the addition of or the reinforcing interface and matrix, this is your Poisson ratio. It basically just tells you that you are stiffening your material in the transverse direction. So you have a better load carrying capacity while you are pulling, your material is being deformed. If you did not reinforce it, then you will not be able to observe this attributes. And we look at basically also the improvement in relation to the impact behavior. It is in the range of 30% for that one. Now, if you look at it, if you summarize all the tests that we have done as a spider web, this is the neat one. The green one is only the interface. The red one is the matrix, but if you reinforce both the interface and the matrix, what you get is really notable. The work of fracture, flexural strength, flexural modulus, impact, tensile strength, and tensile modulus. So you are improving your material significantly without increasing your reinforcement amount of carbon fiber reinforcing materials. And this is the number-wise the summary of that one. We also look at some of the attributes of dynamical mechanical properties, and this is when you look at here, it just gives you better elastic modulus, and this is its TG, which is the tangent delta. The peak of it is its TG. By adding it, you are not just changing significantly the last transition temperature of the material, but you are just basically changing the damping attributes. Whether how well it can just absorb, for example, any incoming deformation wave in your system. I'll just skip this one. Just to basically running this, I'm actually under different frequencies. I'm not going to get into the details of it. But what you can observe is that the energy that is required for inducing the glass transition temperature is being improved. For example, here, this is the amount of energy that you have to provide into the system to induce glass transition temperature. And this is when you integrate your nanomaterial, it can just shift it from the 350 to 400 levels. I'll just speed up, I'll just skip this part. We also look at not only the mechanical properties, but also the electrical properties. The graphene, if it is not defective, it is highly conductive. Carbon fiber is conductive. And we look at the in-plane conductivity of our material. This is your neat material. It is around 30 Siemens per centimeter. And we observe that when we integrate this one only to the interface, we have a notable drop in electrical conductivity. Naturally, you expect that value should increase. Actually, the graphene just acts as an electron traps. It doesn't allow electron to propagate on the highway, and the highway being your carbon fiber reinforcement. Okay? So that is the reason it just basically decreases your electrical conductivity. When you add to the matrix, nothing surprising, because matrix is dielectric material, it is non-conductive. If you add something conductive, it's going to be better electrical conductivity. It will provide better electrical conductivity. But what we observed, if we use the hybrids, so by combining those traps with the ratio of the matrix, that you can increase your electrical conductivity performance almost 4 times. That is huge, because for aircraft applications, for lightning strike, they put a mesh onto the skin of your aircraft. Instead of putting a mesh, because that is the amount of conductivity required, that you can integrate this one. It is going to act as a reinforcement, and it's going to act as a pathway to discharge the lightning strike, so that your laminate is not going to be damaged. So this is, I think, one of the highest result that is reported in the literature in relation to this. And we look at actually by thermography whether these are the cases. So this is the thermography image of our material, and you see that this is not conductive. And then if you put the crocodile ellipses here, you have a lot of heat generation because the current doesn't want to pass through it. And this is interface modified. Again, you have a similar problem. If you have a matrix, it's a little bit better than that. But if you have both, then it gives you a pathway so that you can just basically conduct the electricity problem. Why this is critical? And also we look at by using the pulse thermography. These are the systems available at the center in terms of the facilities. We look at also the improvement is the thermal diffusivity, and this is the thermal diffusivity, although the thermal diffusivity increases, but not that low. So by adding graphene, you are not making your material more the thermally conductive. Slightly better results, but not as high as the case of the electric conductivity. And then we basically apply to this one to de-icing. For aircrafts, in the winter times, you have to use agents, solvents. But if you basically apply a minuscule amount of electric field, if your material is conductive, then you will be able to de-ice it. And this is basically, we just put this one in a liquid nitrogen and form an ice droplet here. And they pass the current for these 4 different materials. And you see that when you have this interface and matrix reinforcement, this is the drop time. It just drops away and slips this one in around, let's say, 100 seconds. And for those, it takes around 200 or 300 seconds. With this part is finished, I would just basically want to give you, because I'm almost running out of time, another 4 minutes, I will give you some examples about self-healing capabilities that we can incorporate into the composites as well. So if you look at many cell phones, actually, they sell you the cover, And those cover when they scratch, it repairs itself. That is called self-healing. Or the body. If you cut your body, the blood rushes there and fixes it, and then you repair yourself. And as engineers, we want our material to be self-healing as well. And for that, what we have done is that we created vascular networks in our composite structure, which is formed by nanofibers. When I say the nano, really they are nanofibers. And those two fibers, one of them contains resin, another one contains the hardware. So when we have a crack in your system, crack comes because the stress at the tip of it is much larger than the local stress. So it breaks the fiber. Those two components, both the resin and hardeners, they leak and repairs the crack region. And that gives you a material that heals itself. And this is the idea actually that we have done, and this is an example of it. So you have a vascular nanofibers that we just do coaxial fiber. We can produce them such that you have liquids. And the inner size of this one is around, I think, 300 nanometers. So we are not injecting the liquid later. We are producing it with the liquid at one stage. I will just skip some of them. These are the details of it. So these are some of the tubes, and you see that this is the inner tube. I think this is, the inner one is the 100 nanometer, outside is 300 nanometer. So one includes epoxy, another one includes amine. And this is like a vascular network, or the blood vessel, in your structure. I will just skip this one. We incorporate it into our composite. I will just basically show you the result. You see that this is your fiber, composite, without any nanofibers or healing. And then we apply bending, and then just basically material is being released and cured. And I've done this one several times. And look at the degradation of elastic modulus. And you see that since this is the green, it loses almost 20% of its initial strength. This is normalized. And this fellow just to basically lose its young modulus only by 10%. So it means that you are able to repair your material. And actually this result is quite interesting that I want to show you. We include in our material fiber brag grating. So it's an effectively optic fiber that brings internet to the door of your house. And it is like a hair, that one. And then we integrate it and look at the crack evolution. And we see that when you repair, when there's a fracture, because you are not able to transfer the strength accordingly, the sensor doesn't read it. But if you repair it, then load transfer is continuous, so your sensor can read it. And it shows that, look at here, the sensor can read the successive healing. Another observation that we have I want to show you, I can skip this one. We look at the acoustic emission data. When each crack is formed, it sends a sound wave, an elastic wave. Initially, your matrix cracks. Later, your delamination occurs through the matrix cracking, then the fiber rupture. If you repair your matrix continuously, it means that you should continuously eliminate acoustic emission. Actually, this results show that for the fourth cycle, still you have an acoustic emission due to the matrix cracking. But this is without repair. Look at here, matrix cracking signals are very, very low. So it indicates that you are fixing your matrix and your composite significantly. So the summary of all this, as a takeaway lesson, if we integrate our composites with the nano-integration properly, and not in an ad hoc manner, and do the engineering, including the knowledge of the chemists, processing engineers, and the signal processing people, then the material can be produced that will far exceed the attributes of an ordinary system. And with this, I believe my time is almost over. I would like to conclude my presentation. And thank you very much for your attention. It will be my pleasure to have your questions if there are any.